Let's talk about how we can identify points of concurrency, as well as special segments drawn in triangles, and also how we can use these things to solve problems. In our previous video, we learned about the differences between perpendicular bisectors, angle bisectors, altitudes, and medians, as well as circumcenters, incenters, and orthocenters, and centroids. The first thing I want us to do in this lesson is look at some special segments that have been drawn inside of a triangle and identify what kind of special segment is it, as well as what would the point of concurrency be called. Looking at this diagram, I see that each of the triangle's angles have been bisected, right? Angle RPQ was cut into two congruent angles by segment PT. And you could say the same thing for each of the other two angles in triangle PQR. The type of segment that bisects angles is called an angle bisector. So all three of these segments must be angle bisectors of this triangle. And we learned that the angle bisectors of a triangle intersect at a point called the incenter. So point S would be the incenter of triangle PQR. We learned that the incenter is equidistant from the sides of the triangle. So if you were to go from point S, the incenter, to side PQ, or side PR, or side RQ, that distance would be the same for all of them. Let's try another example. This time I see some segments that are perpendicular to one of the sides of the triangle. For example, side PQ and segment VR are perpendicular to each other. I notice, though, that V is not the midpoint of PQ. Instead, VR connects side PQ to the opposite vertex such that VR is perpendicular to PQ. We call that an altitude. And since each of these segments are altitudes, they intersect at a point called the orthocenter. Point S is the orthocenter of triangle PQR, because it's the intersection of the altitudes of the triangle. Our next example has perpendicular segments as well, except instead of connecting one side to the opposite vertex, like what we saw in the previous example, this time they're perpendicular and they bisect each side. That makes these perpendicular bisectors. VS is perpendicular to PQ, and V is the midpoint of PQ, which means this has to be a perpendicular bisector. And that means that point S is the point of concurrency of the three perpendicular bisectors, so we call it a circumcenter. And we learned that the circumcenter is equidistant from each of the vertices of the triangle. So RS and PS and QS would all be the same length. In our last example, we see a segment that connects a vertex of the triangle to the midpoint of the opposite side. That kind of segment is called a median, and the medians intersect at a point called the centroid. The distance from the vertex of a triangle to the centroid is 2/3 the length of the entire median, so QS is equal to 2/3 of QU. Additionally, we know that the centroid is the center of gravity or the center of mass for the triangle. So if this was, a piece of paper or something, you could balance triangle PQR perfectly on point S. Triangle PQR, which is what we looked at for the previous 4 examples, was an acute triangle, which meant that all of the points of concurrency were inside of the triangle. However, our next example, triangle WXY, is obtuse. So therefore, sometimes you'll have a point of concurrency like what you see here, which is outside of the triangle. But the process for identifying what it is that we're looking at is the same. Look at each of the segments that were drawn, identify whether they bisected angles, bisected sides, are they perpendicular, are they not, and put all of that information to decide what kind of segment is it. So for each of these segments, I see that it's perpendicular to one of the sides of the triangle, and also that it intersects at the midpoint of that side, because YA is congruent to XA, A must be the midpoint, and ZA is perpendicular to side YX at that midpoint, which means it must be a perpendicular bisector. All three of these perpendicular bisectors intersect at point Z. That point of concurrency would have to be called a circumcenter. And we learned that the circumcenter of a triangle is equidistant from the vertices, so the distance from W to Z, or Y to Z, or X to Z, all of them are the same length. In our next example, we have more perpendicular segments, except this time they don't intersect at the midpoint of each side of the triangle. Instead, they pass through the vertex on the opposite side. That's called an altitude. These altitudes intersect at point Z, which is called the orthocenter. Then we have a few segments that intersect at the midpoint of one of the sides of the triangle and connect it to the vertex on the opposite side. The segment that does that is called a median. And their point of concurrency, point Z, would be called the centroid. And in our final example for triangle WXY, we see segments that have bisected each angle, as indicated by each of these congruence arcs. Therefore, each of these segments must be an angle bisector, and their point of intersection is called the incenter. The incenter is equidistant from the sides of the triangle. Our last triangle, FGH, is a right triangle. Let's see how that changes things. This example shows a segment that connects the midpoint of one of the sides of the triangle to the vertex on the opposite side, and that's called a median, and the medians intersect at a point called the centroid. Remember, the centroid is the center of mass. Additionally, the distance from the vertex to the centroid is 2/3 of the distance of the entire median. Next, we have some segments that bisect each angle. Therefore, they're called angle bisectors, and they intersect at point I, which is the incenter. Next, we have somewhat of a strange example because it looks like only one segment has been drawn. But let's break down what we're actually looking at. Segment LI is perpendicular to one of the sides of the triangle, and it connects to the vertex on the opposite side. So we can identify that this one segment is an altitude. But where are the other altitudes? Well, in order for us to draw a segment that is perpendicular to side IG and connects to the vertex on the opposite side, it would actually just be this side length of the triangle. FI is simultaneously a side of the triangle, as well as one of the altitudes. Likewise, if I wanted to draw a segment that is perpendicular to side FI and connects to the vertex on the opposite side, again, that would just be one of the sides of the triangle. So side IG is simultaneously a side of the triangle as well as an altitude of the triangle. So these two sides, as well as this segment, intersect at point I. That makes point I the orthocenter of this triangle. And the final example here is similarly kind of confusing because I only see two segments drawn inside of this triangle. So what's going on? Where's the other special segment? We usually have three. Well, let's look at least the two that we have drawn and see if we can identify what they are. Each of these segments are perpendicular to one of the sides of the triangle, right? KI is perpendicular to FH. Also, K is the midpoint of that side. So that means that these segments are perpendicular and they bisect, so they're called perpendicular bisectors. And that's easy to see for this side, that you find the midpoint and you draw a line that is perpendicular from it. And you find the midpoint of side HG and you draw a line that's perpendicular from it. And they intersect at point I. So then I don't really have to do anything else to find my point of concurrency, because if I look at side FG and I find its midpoint is point I, where the other two perpendicular bisectors had already intersected. So there's no need to draw something that's perpendicular from there in order to find the point of intersection with the other two lines. Those two lines already intersected with point I, and therefore I'm done. I don't actually need to draw a perpendicular bisector here. Therefore, point I is the circumcenter of this triangle. So let's use these special segments and points of concurrency to solve for some missing side lengths. The first thing you should identify is what kind of special segments are you looking at. And in this case we have medians, because each of these segments, such as WA, connect a midpoint of one of the sides of the triangle to the vertex on the opposite side. And we've learned that the distance from a vertex of the triangle to the centroid is 2/3 of the distance from W all the way across to A, which would be the median of the triangle. We can use that information to help us solve for some missing side lengths, in addition to the fact that we have some congruence marks already. For example, YX is this entire side length, and I was given that YA is 20. Well, if YA is 20, then XA is 20 as well, right? These have the same marking, so therefore they must be the same. And if I'm asked to find the entire length of YX, then I would just add 20 and 20 to get to my answer of 40. But now let's calculate the length of ZA. ZA is part of median WA, and we were told that WA is 42 inches long. And remember, the relationship between the centroid and the entire length of the median is that the distance from the vertex to the centroid is 2/3, which means the distance from the centroid to the midpoint is 1/3. And I know the entire median is 42. ZA must be 1/3 of that. So ZA is 14. Now let's try to solve for YZ. All we know is that CZ is 11. If I put CZ and YZ together, I get to an entire median. Remember that the relationship is the distance from the vertex to the centroid is 2/3 of the entire median, or that the distance from the centroid to the midpoint is 1/3. In other words, CZ is 1/3 of the total. I'm looking for 2/3 of the total. So it makes sense just to double what I have. If I have 1/3, I can double it to get to 2/3, so YZ must be 22 inches. Finally, let's solve for... Oops, sorry about that. I want you to actually solve for XB. There we go. Let's solve for XB. It wouldn't make much sense to ask for XZ, right? Because I already told you ZX was 36. So ZX is 36. I want to know what is the length of the entire median. Well, I know that the distance from a vertex to the centroid is 2/3 of the entire median. And I know that that 2/3 length is 36. Well, I need to add another third onto that. Well, if I know 2/3, I can figure out 1/3 by taking half, right? Half of 36 would be 18. So each of the thirds is 18, so I would get to a total of 54 inches for the entire median. Let's try another example. Here we see a few different segments, and it can be kind of confusing to identify what am I actually looking at. Because I see two different kinds of markings. I see some angle congruence markings, as well as some right angle markings. The right angle markings might make you think of perpendicular bisectors, but take a quick look at your side lengths and notice that O is not the midpoint, so this OS couldn't be a perpendicular bisector. But could it be an altitude? Altitudes are perpendicular, but they don't intersect at the midpoint. They go through the vertex on the opposite side of the triangle, but this also doesn't go through that vertex. So these perpendicular segments are none of the special segments that we talked about. Instead, let's look at the other segments that we have. For example, PS bisected angle P, and RS bisected angle R, and QS bisected angle Q. So what I'm actually looking at here are some chunks of an angle bisector. So then what are these perpendicular segments? Well, remember we learned that the incenter, which is the point of concurrency of the angle bisectors of a triangle, the incenter is equidistant from the sides of the triangle. And as we've discussed in previous units, the shortest distance from a point to a line is the perpendicular distance. So all that these three little perpendicular segments are representing is that shortest distance from the incenter to each side of the triangle. So let's take a look and see if we can solve for the missing angles and the missing segment length. First we want RPS. RPS, that's this little angle right here. And we were given that QPS is 38. QPS is this angle. These two angles are marked as congruent because PS is the angle bisector, so RPS must be 38 because QPS was 38. Next we want angle PQR. And we were given that angle PRQ, this entire angle down here, is 78. Well, remember that triangles always add up to 180 degrees. So since I know that angle QPS is 38, that was given, and we calculated that angle RPS is 38, and we were also given that PRQ is 78, I can just subtract those three angle measures to figure out that PQR must be 26. The last thing we were told is that NS is 12. NS is the distance from the incenter to one of the sides of the triangle. And we know that the incenter is equidistant from the sides of the triangle, therefore MS must be 12 centimeters. In our next example, we have perpendicular bisectors drawn. Well, at least two of the segments are perpendicular bisectors. KI and JI are perpendicular to each of the sides of the triangle, and they are bisectors of those sides as well, and that makes KI and JI perpendicular bisectors. However, HI is not perpendicular to one of the sides of the triangle, so what is it? Well, remember that the perpendicular bisectors of a triangle intersect at a point called the circumcenter. I is the circumcenter of this triangle because it's the point of intersection of KI and JI. The circumcenter of a triangle is equidistant from the vertices of the triangle. So that means that the distance from I to F, and I to G, and I to H are all the same length. The segments from I to F and I to G didn't need to be drawn on the diagram because they were already there. They're the hypotenuse of the triangle. However, the distance from I, the circumcenter, to the other vertex, the third one, point H, that had to be drawn on there because it didn't already exist. Okay, so now that we know what we're looking at, let's see if we can figure these things out. We're going to start with the measure of angle G. Now all we were told is that angle F is 64, but that should be plenty of information to figure out angle G because it's a right triangle, so according to the corollary to the triangle sum theorem, angle F plus angle G must equal 90 degrees. So since F is 64, G must be 26. Okay, well what about JG? Well, we were told that HJ was 53, and it's marked on the diagram that HJ and JG are congruent, so that means that JG must be 53 feet. Then we're supposed to calculate the measure of FI. FI is marked as congruent to GI, but I don't know either of those lengths, and I don't know the entire length of FG. The only other length that I was told is that HI is 60. Well, HI is the distance from the circumcenter to a vertex of the triangle. And since I is the circumcenter, we know that it's equidistant from each of the vertices. So IH is the distance from the circumcenter to each vertex, and IF, or FI, is another length from the circumcenter to a vertex, which means that FI must be equal to HI. Likewise, GI must be equal as well. Okay, let's see how these points of concurrency and special segments in triangles can be applied to real-world problems. Tyrell likes building unique furniture. He is working on a triangular table shown below. If he wants to support the table with a single leg placed at the center of the tabletop's mass, where should the table leg be placed? Well, remember that we learned the centroid of a triangle is also its center of mass, or center of gravity. So what we need to do is draw all of the medians of this triangle and identify their point of intersection. In order to draw the medians, you need to find the midpoint of each side of the triangle, which would be each of these points. This point is halfway in between each of these vertices, this point is halfway in between each of these vertices, and this point is halfway in between each of these vertices. Next, we will connect each of those midpoints to the vertex on the opposite side. So that point right there is where Tyrell should affix a leg in order to balance the triangle tabletop perfectly. In our next example, we have a few different islands that grow different things. Island A grows apples, Island B grows bananas, and Island C grows cantaloupes. And the settlers from each of these islands get together to trade their fruits. If all three islands send out a boat full of fruit to trade with the other islands, where would be the most fair place for them to meet? In other words, what is the equidistant place from all three islands? Well, remember that we learned that the circumcenter of a triangle is equidistant from the triangle's vertices. And if we imagine that each of these islands is a vertex of a triangle, then all we need to do is find the circumcenter of the triangle, and that would be the most fair place for these traders to meet. In order to find the circumcenter, we need to draw the perpendicular bisectors. So we'll start in a similar way to what we did with the medians on the previous problem, which is to say we'll find the midpoints of each side. So find the halfway point between island A and B, the halfway point between island A and C, and the halfway point between island B and C. But unlike what we did on the previous example with medians, I'm not going to connect those midpoints to the island. Instead, I'm going to draw a line that's perpendicular from that point until all three of them intersect. So each of these three yellow lines intersect the midpoint of the dotted lines that connect each island, and they are perpendicular to each of those dotted lines. The point where they intersect is called the circumcenter, and that is equidistant from each of the islands, so each of the boats would travel along each of these red lines until they meet the point in the middle, and therefore they would all be traveling the same distance, and therefore it would be the most fair route. And in our final example, we're going to help plan a park. The map below shows 3 paths in a park, and the city has decided that they want to put a pavilion somewhere in between all of those paths. And they plan on building a new short little path leading to the pavilion from each of the paths that already exist. So where should the pavilion be placed so that the paths connecting from the pavilion to each path are the same length, are equidistant? Well, remember that we learned that the incenter of a triangle is equidistant from the sides of the triangle. So all we need to do is find the incenter of the triangle created by the paths. To find the incenter of a triangle, you need to bisect each angle. This line would bisect one of the angles, this line bisects the other, and this line bisects the third angle. Each of these 3 lines cut each angle in half, and they intersect at a point called the incenter. The incenter is equidistant from each of the sides of the triangle, so the paths that they should draw are each of these distances, which go from the incenter along a perpendicular distance to each of the existing paths. The yellow point is where the pavilion should be built. And that's all you need to know about incenters, circumcenters, orthocenters, and centroids. And that actually wraps up our triangles unit. In our next unit, we'll be discussing similarity and proportions.